in this episode of Street Talk Unplugged.
So the free energy principle originally emerged from systems neuroscience as a principled way of understanding what the brain does and how it does it. Subsequently, the principles proved to be so simple and so powerful that they've been applied in a variety of contexts now. So one could almost regard the free energy principle as an organizing principle for any living system that shows the characteristics of life.
In this episode, we'll be doing a bit of epistemic foraging with Professor Karl Friston, legendary neuroscientist and inventor of the free energy principle.
The basic idea is that our brains are in the game of predicting sensory inputs to try and infer the causes that generate sensations and to work out states of the world so that we can respond adaptively.
Now, long ago in my own personal epistemic journey, I learned an important truth that simple and easy are not the same thing. Our shared human journey is filled with examples of simple ideas that were, nonetheless, hard to discover, and some that even once explained remain hard to comprehend. Their subtle simplicity belies their far-reaching and deep consequences. Examples might include the principle of relativity, quantum mechanics, the principle of parsimony, and entropy. I think the free energy principle is another example. Profound and far-reaching, yet belied by its simplicity. It has, on the one hand, been dismissed as a triviality or even a tautology, and on the other, hailed as revolutionary, and everything in between. It has the potential to reshape how we view the connection between inanimate matter and living things, and even to answer the question of how and why consciousness and intelligence might emerge from physical matter and processes. There are, of course, newer attempts to explain the free energy principle, such as Karl's own recent paper called The Free Energy Principle Made Simpler, but Not Too Simple. The paper develops by starting from a world modeled as a stochastic differential equation. Now, leaving aside the technical jargon, that means a world where all things, from particles to people to the largest systems, all move or evolve according to two processes which combine. The first is a smooth-flowing evolution. Think of planets orbiting a star, or waves rippling over water or through quantum fields. The second is a random process that knocks around the smooth flow in unpredictable ways. Think of twinkling stars or audio static. You might think of these two processes as a kind of order and chaos, or yin and yang, forever intertwined and enmeshed. These two very different effects combine into a chaotic flow, which may be entangled in a kind of tropical storm, while still maintaining a semblance of structure and things. Think about raindrops undulating down to earth in a state of constant flux, yet still droplets. Or a human being growing and adapting to the surprises of life, all the while remaining an individual, physical entity. Biology often asks the question, what must things do in order to exist? Professor Friston has turned that question on its head and developed perhaps the ultimate existential formalism. He asks, if things exist, what must they do? From the foundation of stochastic differential equations, Friston demonstrates that things, which are defined by a Markov blanket, must always move towards a pullback attractor, a special set of attracting states which maintains the integrity of the Markov blanket and therefore a thing's coherence and identity over time. One of the profound consequences of this is that the dynamics of such a system, its laws of motion, will manifest a form of flow dynamics which can be interpreted as Bayesian active inference. In other words, such a thing maintains an internal equivalent of a generative model encoding beliefs about the world and itself. The thing uses the model to decide actions and then performs a Bayesian update based on the outcomes. For me, the idea that inference, something widely perceived as purely abstract or mathematical, the idea that it can be driven by simple laws of motion, dynamically maintaining the boundaries between things, maintaining order in the face of chaos, is frankly astonishing. What's more, the free energy principle is so general that it applies at all scales of size and time, leading to an ecosystem of things interacting across scales. Perhaps in that multi-scale active inference, we might finally find the keys to a mathematics of emergence and consciousness.
So, it's so good to see you. It's been, about a year since our show, and I've been looking forward to chatting with you.
It doesn't seem like a year. Yes, I suppose it has been years.
Yeah, it's been almost about a year, actually, a little bit longer.
Time goes very quickly during the coronavirus. Are you all back up to normal now, or still restricted?
Kind of not back up to normal. Still some restrictions, and they change very often, and it's a bit confusing, but it's more normal than it was. I'll say that.
That's an interesting concept, right?
By the way, I just listened to your Kurt's Theory of Everything podcast.
Right. Was that the 4-hour one? There was a very long one.
I think it was at least 3 hours. It was the one where at the end you were talking about derealization and depersonalization and getting into psychology.
Well, almost psychotherapy, if I remember correctly.
Yeah, psychotherapy. That's a better way to put it. Quite often, because we do say this about you, Karl, that you have a burden of knowledge. And we mean this in the nicest possible way. So you always know 5 synonyms for a word in every single domain of science. And also, I mean, you even have a background in psychotherapy, so it does create a tendency for conversations to potentially go anywhere. And when we listened to Kurt's interview of you last time, I was really surprised that because we prepared a lot for our session with you, Karl, and Kurt was asking some really open-ended questions that were on the surface quite naive questions, but they elicited the most interesting responses from you. So it really made us rethink a little bit how we do everything on our podcast.
Yeah, I suspect that part of that free-ranging beauty was the fact that there was no hard limit on the time. I had no idea. 3 hours, but he was a very engaging young man. And I think part of that open-endedness was deliberate. He was just
right.
Indulging a bit of epistemic foraging.
Well, it's funny you say that, because that's the free energy principle in a nutshell, isn't it? That we need to balance the entropy.
Back to this burden of knowledge, because I want to ask you a little bit about that, which is and I find this is often the case. Say for example, a kid comes and shows you a test that they're taking, and there's a math question on there, right? Now, when I was their age, I could have answered it quite easily, but as I learned more about mathematics and engineering, now I look at the question and I'm sitting there thinking, yeah, but there's all these assumptions. Like, how do you know this variable's positive? Maybe it's negative. Like, it could be a real number. You have all this extra knowledge that's entering in and impinging, if you will, on the ability to answer that question. And so I think a lot of the times when you're asked a deep question, I'm imagining because your depth of knowledge and breadth of knowledge is so large, you're sitting here thinking, okay, how can I answer this in a way that's precise and accurate? And so therefore it requires the use of technical and, accurate and precise terms. But then for the person hearing that answer, they may not have, the requisite knowledge of those terms. And so it seems as if it's coming across as obscure or something. Like, do you run into that? Do you run into that often?
Yeah, no, well, I think we all do, don't we?
Yeah.
Talking across disciplines, you've got to get that. You've got to find the narrative that works. In a sense, if you're taking a sort of a free energy principle approach to this, you're trying to establish some kind of generalized synchrony, which so that my narrative becomes your narrative. But that mutual understanding does require a commitment to the same rhetoric, the same calculus.
Right.
So you're often putting a lot of theory of mind, a lot of perspective taking, to the extent sometimes you have to sacrifice a degree of precision. If I wanted to articulate something that I know I could simulate or write down mathematically, it would just take the kind of language which was not part of the portfolio of the person I was talking to go through properly. So, you just have to take shortcuts, heuristics, and priors and the like, which is part of the art. It's back to Einstein, keep everything as simple but as possible, but not too simple. That's the art of the...
Well, in a bit, we're going to ask you about your most recent paper that literally has that title. Almost the free energy principle made simpler, but not too simple. So we're going to ask you about that later.
Indeed we are. And it's interesting what you say, Karl, because you're talking about things which are so alien. It might seem that you're pointing out the obvious when you talk about self-evidencing or when you talk about the basics of probability theory. But Keith and I often remark that a lot of people just don't understand probability theory, a lot of very smart people. And it might seem that we're reducing it down to the most basic principles, but they just can't be articulated very, very clearly.
Yes, and people like me sort of lose sight of that. There are some basics you assume people do know, but of course it takes years before you're fluent and have all the right intuitions. So that, I think, in part is an explanation for why people like me are so often cast as being impenetrable or very difficult to understand. Well, it's not, but it probably reflects, again, a lack of theory of mind in terms of being able to, understand what people do know and don't know.
Wonderful. Well, I'm going to officially introduce you, Karl. Professor Friston is a British neuroscientist at University College London and an authority on brain imaging. In 2016, he was ranked the most influential neuroscientist on Semantic Scholar. He pioneered and developed the single most powerful technique for analysing the results of brain imaging studies, and he's currently a Wellcome Trust Principal Fellow and Scientific Director of the Wellcome Trust Centre for Neuroimaging. His main contribution to theoretical neurobiology is the free energy principle and its Bayesian reinforcement learning flavour, active inference. The free energy principle is a formal statement that the existential imperative of any system, which survives in the changing world, can be cast as an inference problem, the probability of existing as the evidence that you exist, if you will. This is what Karl refers to as self-evidencing or even autopoiesis. Now, the system, of course, could exist at any scale or time, and as you might well imagine, this will lead us directly into a discussion on complex systems theory, self-organization, and emergence. But anyway, Professor Friston, it's an absolute honour to have you back on the show. Welcome.
Thank you very much. It's great to be back talking to you again. Oh, and incidentally, a great summary of the free energy principle. Was that from Wikipedia or something slightly more learned?
Well, we like to interpolate from multiple sources, Karl.
Yeah. If we can just jump back actually to what we were talking about with things that are simple that may still be hard to understand. If I may, I want to share an anecdote with you. And this came to mind when I was reading a recent paper, The Free Energy Principle Made Simpler, but not too simple. And the first line of the introduction says, "It is said that the free energy principle is difficult to understand. This is ironic on 3 counts. First, the free energy principle is so simple that it is almost tautological. And what occurred to me there was one of the most valuable life lessons I got in graduate school was I was in a cryptography and cryptanalysis class, and it was being taught by Professor Silvio Micali. And he's since gone on to quite some fame in the cryptographic space. And the first day of the course, okay, he puts a secure communication problem on the board. The very first thing that he does on that day, puts a secure communication. These are kind of like brain teasers in a way. You have to come up with a way to solve this problem. And he goes, okay, does anybody know how to do this? Somebody raises their hand and gives them an idea. And he goes, no, that won't work. Here's why. And he shows how to crack that. A couple minutes later, another student, how about this? 2 random numbers, communicate. No, that won't work either. Here's how to crack that. Right. And so after about 5 or 6 attempts from the class, maybe 15 or 20 minutes, nobody could solve it. And he goes, okay, this is the perfect place to begin this course because I'm going to show you the answer. And when I do, it's going to be so simple that you're going to say, ha, that's easy. No, something that's easy is easy from the beginning. If somebody has to tell you the answer, it's only simple. Right. And I think, human history is just full of examples of ideas that are very, very simple, yet took, the combined intelligence of humanity thousands of years to discover. They may be very simple ideas, but they're still very difficult to kind of grok, to really internalize and understand. And I think we have those all over science, and the free energy principle may well be one of those. So even though it may be very simple, it could be difficult to kind of cognitively grasp. And I'm almost starting to think over the last year or so that human cognition itself, like in the cognitive space, there's sort of this Markov boundary between an external world of ideas and internal. And there's a fluctuation there at the boundary where sometimes the most advanced ideas, they may creep into what's in our sensory range and we can just grasp them, but then they kind of fly out again. And they're just always on that cusp of what we can really understand. Just curious what you think about that.
I think that's a very compelling formulation of and I've never heard that before, the distinction between easy and simple. As you were talking, I was mindful that everything you said could in one way be applied to evolution. And indeed, in terms of the evolution of ideas and the scientific process itself, cast as encultured evolution, sort of co-evolution or evolutionary psychology, as one special case of the evolutionary process. You could argue that evolution is solving a really difficult problem to disclose a really simple solution. And that simple solution, of course, is you and me, just finding the simplest phenotype artifact that fits with the eco-niche that is co-constructed by other artifacts and simple constructs, Markov blankets, that constitute that eco-niche. I think that's a wonderful insight. And the simplicity bit, I think, is really quite crucial in the sense that, let's take the cryptography or cryptanalysis. I'm mindful of one of the very first introductions of variational free energy by David McKay, who just applied free energy minimization to the problem of encoding and cryptanalysis from the perspective of minimum description lengths and compression, which speaks to an alternative view of the imperatives for any efficient representation or evidence accumulation or data assimilation scheme or communication scheme. In the sense that you can either read the history of this from Richard Feynman and the pathological formulation of quantum electrodynamics, or you can go right back to algorithmic complexity, Kolmogorov complexity, Solovov induction, through to minimum description length compressibility, and right through to universal computation. Both at their heart have this notion of simplification aspiring to or converging to a minimum complexity, a minimum description length, a maximum compressibility. So if you read you and me as the products of evolution that are the most efficient installation of all the information that I need to engage with this eco-niche that we have co-constructed, then exactly the same principle emerges. I guess what you're saying is, and I think you're absolutely right, that those kinds of principles not only apply to our structural phenotypes and the functional architectures that we have in our brain and indeed our bodies, but also the cultured constructs, what people like Cecilia Hayes would call cognitive gadgets, the things that beyond a canoe, which has evolved, but in a way very differently from the way that you and I have evolved, beyond that to things like language itself. Where did language come from? How does that simplify our sense-making and efficient representation of a causal structure in the world? So I think there's some really profound common themes, cross-cutting themes in that description. And in a sense, of course, spotting, which is not easy, but spotting those simple cross-cutting themes is exactly the process that that you're talking about.
Right. And I often get the feeling that that many of us or many researchers out there are all orbiting this kind of central truth. And it's not just there are the cultural constructs, the physical constructs, and some abstract concepts that are somehow grounded in the core, reality of physics and the universe. And I feel like we're all orbiting them, and we haven't quite gotten there yet. I think the free energy principle may be the closest, but there's still gaps. There's still things that we don't understand. There's still missing parts. And it'll be really interesting when somebody finally locks them all together and grasps that simple connection of them all.
So how will you know when they've done that?
That's a good question. How would you know when you've done that? I guess for me, it would be when we really have a mathematics of cognition. So it's close, but still far away in a sense.
Yeah, I agree entirely. And that simple point, having that, if you're committed to this notion that there is an evolutionary process in play, which in my world I would read as nature's way or natural Bayesian model selection, or optimizing your explanations for the world with respect to the evidence, the Bayesian model evidence for that. So I look at natural selection as the process of Bayesian model selection. And interestingly, just coming back to your example in your first class with your well-respected professor, he was illustrating there, I think, the process of Bayesian model selection by putting forward alternative hypotheses, eliciting them from the audience, and then evaluating the evidence for them by, in this instance, falsifying them because that particular strategy was easy to crack. But illustrating that this is a process of selection, and also evincing a deep problem, which is generating the hypotheses, the models, the phenotypes from which to select. So I think that's why I think the evolution perspective is so compelling. Speaking to issues, the difficult problems, which I think in radical constructivism would be known as structure learning. It's easy to score a good structure, a good idea, a good explanation, a good hypothesis, a good bit of code algorithm. It's easy to score how good it is, but to actually create a portfolio or an ensemble of alternative to build a hypothesis space in the first place, that's the uneasy bit, that's the difficult bit, because what we're talking about is just being a good scientist. It's asking the right questions by having the right kinds of hypotheses for which then you go and search for evidence. Again, that was a very nice example to bring to the table. Now I've completely lost what we were talking about. What did you bring to the table with your question?
Oh no, it was just a comment that that we all should take care that simple concepts can be very, very hard, and furthermore, simple concepts can be extremely valuable. So the the two lessons I learned there were that simple and easy are not synonyms, and simple and trivial are not synonyms.
And you also highlighted the importance of a precise and simple way of expressing those ideas in terms of mathematics. I think, and I'm tempted to ask you, but I won't. But why mathematics? And perhaps mathematics is the simplest, most self-consistent calculus language that you could adopt. Furthermore, it is the kind of language that you could use to communicate and share, in the sense of this cultural approach to coevolution with people who don't speak your native language. With your Vietnamese colleagues, or people who don't actually communicate it in narrative form, but you can still, in a very precise, unambiguous, simple way, express those ideas and those hypotheses, even mathematically, and it will still be understood and have meaning for somebody in another culture, in another world, speaking another language. So I on that view, if you had to commit to a particular language, that it really has to be mathematics, which is actually a bit worrying in the sense that not everybody is mathematically fluent, which brings us back to you have to understand certain simple mathematical fundamentals before you can even start talking.
Yeah. Although interestingly, it's a little bit like Tetris. So you don't need to understand that many fundamentals about maths until it has an extrapolative effect in many different parts of experience space, if you like. But Professor Friston, I wanted to talk a little bit about the low road and the high road. You often say that the low road is the mechanistic view of predictive coding and neurons in the brain and all the low-level stuff. The high-level road being the emergent and the self-organizing phenomena. Let's just do the low road first. We want to get to the high road later. But we just had a wonderful conversation with Professor Yoshua Bengio, the godfather of deep learning, and he's doing something very similar to you. He's got this invention called G-flow nets, and he's using that in place of the variational inference technique that you're using in active inference to compute the free energy. G-flow nets can be thought of as a drop-in replacement for Markov chain Monte Carlo for computing unnormalized energy functions, but without the handcrafted priors. And even if the modes in the energy function are thin and far between and in a high-dimensional setting, it's a kind of machine-learned version. I think you'd find it very interesting. But anyway, Bengio is also a huge fan of this distributional reinforcement learning and balancing entropy in a principled way. And when I pointed out the obvious similarities to your work and active inference, he spoke very positively. So you need to check that episode out.
Lovely. I will do so. Yeah, I'd never heard of that, but that, I have heard him talk before. I do get a sense he is certainly becoming more of a physicist as he gets older. A probabilistic physicist, I should say. Yeah, that's very nice.
So what's changed in the last year for the free energy principle?
Let me think. Well, one thing that, interestingly, that we've been working on is indeed this communication and trying to sort of get towards a simpler exposition that people can more readily access and use in their own setting. Part of this is entails spotting what the important, simple contributions are, and what it can do and what it can't do, what it's there for, what it's not there for. So trying to pare back the fundamental parts of it from those secondary auxiliary issues which are more interpretational in nature. So from a technical point of view, it's just been staring at the ideas, thinking about the ideas and saying what is the absolute essence of this, and trying to articulate that mathematically as simply as possible, but not making it too simple. The one technical aspect here is what is the precise role of the Markov blanket, and to what extent does that rest upon the notions that you would inherit from complex dynamical systems theory relative to a more probabilistic construction of the kind that, say, Judez-Pearl's formulation would speak to. Probably more importantly, how does one relate to the other? So how does a sparse coupling of a dynamical sort lead to certain forms of conditional independence? Those conditional independences then underwrite the probabilistic formulation of the coupling between inside and outside of a Markov blanket, which is at the heart of the high road to thinness and self-evidencing and the free energy principle. So that's certainly been a focus. I have to say, slightly inspired by skepticism not from mathematicians or machine learning or artificial intelligence, but from philosophy. So philosophers become very exercised about these things and like to drill down on the precise implications of anything that they understand when they read the math. And certainly one thing which has caused puzzlement in that field is how do you constitute, or where do you place a mathematical description in terms of complex dynamical systems theory, and in particular the theory of random dynamical systems? How do you place that in relation to more conventional conditional independence, sort of Pearlian Markov brackets? So a lot of work has been focused on that. And just for your interest, the upshot of that is possibly going to be a move away from casting things in terms of non-equilibrium steady states, casting things in terms of the probability distribution of a system, a Markov blanketed system at t equals infinity, as the underlying, if you like, aspiration, the probability densities that prescribe and shape behavior. A move back to the much simpler formulation in terms of Lagrangians and path integrals. So this actually is a nice reflection of this, trying to get back to the kernel and the simplicity. And interestingly, in this instance, right back to the inception of certainly of my reading of history of variation free energy in the context of the path integral formulation. So just getting right back to what is the Lagrangian. What is the generative model under the hood? How is that manifest in the equations of motion? And what does that look like in terms of the implicit information geometries that come from the probabilistic concomitants of these random dynamical systems? So I imagine we were talking previously about the most recent attempt to simplify and demystify the free energy principle. Before that paper was actually put on archives, there's another one, which is even simpler, much, much simpler, that just eschews all the delicate issues of non-equilibria or non-equilibrium steady state densities, and just sticks and tries to pursue the whole story from front to end, using purely the notion of a Lagrangian and path integral formulations. So technically, that probably isn't terribly interesting from your point of view, or possibly even your viewers, but mathematically, it's been a real gain, getting back again that difficult process of getting it simpler and simpler and simpler. So that's certainly one thing that's changed. If you're asking me what's happened in terms of uptake and application of these ideas, then I think things are moving more quickly than they were a year ago. And I'm talking here about the application of, or the corollary in terms of your process theories, or the way things work, or the way that you might want to build artifacts or algorithms, which is the active inference. So certainly there's been a much greater uptake and interest in active inference that I've seen simply by pressure and number of emails and conferences and workshops. So literally, I think 2 or 3 days ago, there was a wonderful workshop at the Berlitz School of Mind and Brain, which was just about active inference and free energy principle, and a bit of philosophy at the end, which was an interesting mixture, a cocktail of intellectual challenges. But I was really impressed by work which I had no idea about, that was ranging from simulations of declarative memory, actually getting little synthetic subjects in a computer to actually told you why they made a choice. So you're taking sort of fairly standard economic games, or the kind of paradigms that people in reinforcement learning might use, but having an epistemic aspect, so seeking for information to optimize their decisions and their choices later on, but then taking the active inference framework and then putting on top of that the ability to declare and explain why these decisions were made, leveraging what distinguishes active inference from reinforcement learning, which is that under the hood you have an explicit representation of belief structures. So there is a belief-based approach to any decision or any move that you might make, and you can use that to actually get certain choices of decisions and actions to disclose the belief state. So essentially you can get the computer to tell you why it did that. So that was a wonderful example. Great stuff going on in robotics and neurobotics. Well, I say great because of my sort of colloquial, probably sort of quite narrow view of it, but I'm really impressed with what these people are doing. And what they are doing is just taking as read off the shelf the particular objective function that underwrites active inference, which is the expected free energy, and then thinking, well, okay, how can we scale this up? How can we make this work? And they're bringing things like amortization and all the latest machinery from deep learning, machine learning, to amortize some of the more delicate problems of mapping, say, from high-dimensional inputs to the beliefs as quantified by the sufficient statistics of distributions. Very much in the spirit of a variation autoencoder that actually has at some level a very simple belief structure or posterior belief associated with the values of certain nodes in certain layers, but taking it into the realm of state space models where you've actually got an ongoing dynamics and engagement, as the robot has to have, with the environment, and of course the added and beautifully challenging aspect of robotics, which is the inactive aspect, that it's not just a question of making sense of the data quickly and efficiently in a belief-based way, but using that kind of data assimilation in order to decide what's the best next move that will enable you to assimilate your data better under certain constraints, which of course are particularly prescient in robotics. So that was very interesting. I've noticed there's been a move coming back to the original theme of communication and mutual understanding between disciplines and between people trying to take these ideas forward and converge on the end point, which we might not know when we've got that. But the simple practical things like in my world, much of the proof of principle and the demos that try to unpack and render transparent and accessible the basic ideas are written in academic software, usually MATLAB. And I wasn't aware of this, but no one else uses MATLAB anymore. So, I'm pre-millennial, but apparently you're meant to use Python and Julia and all sorts of things.
I'm afraid so.
Well, actually, hey, use whatever tool works. Well, first of all, I'm excited to see that you're seeing more uptake of the free energy principle, because I think, both Tim and I, after our show last year, have, now we're seeing it everywhere. Like, I mean, we're seeing the concept everywhere. It's like everywhere we look, we think, oh, there's a connection here between what we're talking about now and the free energy principle. So I'm certainly a fan of people definitely thinking about it more, trying to come up with practical systems based off of the principle. I want to come back a bit to what you first talked about, which is the mathematical developments or exposition, if you will, of the free energy principle. And I did mention, the free energy principle made simpler, but not too simpler, which is apparently yet a less simple version than a simpler version that you had also published, which I haven't looked at. But what I loved about the paper that I did look over is the formulation of this as stochastic dynamical systems that are, orbiting around a pullback attractor. So they are trying to get to this attractor. Of course, they're never going to arrive there, and that was a very important point that you made in the paper. That hey, look, this idea that let's say life is conducting an optimization is a bit technically incorrect. It's not doing a formal optimization over the entire marginal distribution. It has a set of dynamics that it follows. So there's a dynamical system that's kind of going, let's say, in a sense, downhill, towards this optimum, but it's moving around. It's being perturbed by external variation, et cetera. So you get this kind of wandering around the attractor. And you said that, philosophers get very worried about how do you connect, systems like that to inference or to probable inference. And you give a connection, I believe, at least if I read correctly in that paper, that you did actually give a mathematical connection between let's show how you can take the dynamics of the system and map it exactly to inference. So I believe that connection is provided in there. Is that correct?
No, that's absolutely right. And indeed, it is just that connection that is the free energy principle.
Oh, okay.
And in a sense, in the sense that we're talking about, it does not surprise me that you are seeing that very simple construct emerge in many, many different fields and many guises, because that's the whole point of just trying to evince something that has this cross-cutting aspect, that you should, for anything that works, in the sense that it persists in the context in which you place it, then it must possess these properties. So what you've just said, which was a very concise and erudite summary of the contribution of that paper, is just an expression of things that persist or things that exist. So, how would you write that down mathematically? Well, if they exist over a certain period of time, then they have to have an attracting set. What kind of attracting set are we interested in? Well, we want the most generic, accommodating mathematical description of systems that does not, I should just qualify this, that does not go quite as far as a quantum mechanic background-free description, but as close as you can get without going going to the other side. And that's a random dynamical system. So what is the attracting set in a random dynamical system? It's a pullback attractor. So you're starting off with, well, okay, so we're talking about things that exist in any given context, in any given setting. Thingness has to be defined. That's the Markov blanket. What does that imply, having a Markov blanket? Well, if it exists sufficiently long for you to be able to, for the conditional independencies to be expressed so that you can write down or assert that there is a Markov blanket, then you have to have a degree of persistence or existence. So thingness entails persistence over time. That entails and necessitates then the pullback attractor. Just sort of picking up on your on the sort of the possibility of over-interpreting the role of a pullback attractor, in the sense that, of course, the definition of a pullback attractor would really be the attracting set that attracts all states as t goes to infinity. Is that a really relevant construct when we're talking about real systems that have an itinerancy, a separation of temporal scales? And as soon as you invoke a separation of temporal scales, which you would have to talk about the difference between inference and learning, learning and development, development and evolution, are you licensed now to restrict yourself to a random dynamical system of the kind that could be written down by a Langevin system with an attracting set that may that requires t equals infinity for its definition? And clearly not. So you have to, I think, sort of confront the certain interpretations of how you are using this notion of a pullback attractor. And that's certainly been something that's been going on in the past year or so now. Largely in conversation, I repeat, with people who are mathematically fluent, but their primary agenda is more an interpretation and philosophical interpretation. And what's come out of that, certainly one motivation for that kind of discussion, is this notion of separation of temporal timescales. So in a nutshell, we've stopped talking about self-organization to non-equilibrium steady state, because that implies that we're waiting until a system has reached t equals infinity and is at steady state. And that's never what was in mind. We were using the steady state and the notion of an attracting set simply to say that this set of differential equations has a solution that is non-trivial, in the sense that the states don't go off to plus or minus infinity. So if they don't go off to plus or minus infinity as time proceeds, then there must be an attracting set. There must be a solution, a non-trivial solution. And it so happens one can interpret that non-trivial solution in terms of a non-equilibrium steady state solution if you've got a Markov blanket that endows it with the fingers, and you've got solenoidal flow to make it a non-equilibrium as opposed to an equilibrium steady state. And then the question comes, okay, so if you're just using the notion of a pullback attractor and its implicit steady state solution to the density dynamics, do the density dynamics in and of themselves have any mathematical or teleological role in them? And can they possibly, if this object is only defined in the infinite future? So what you do then says, well, no. All we meant was, for a suitable period of time, there are certain equations of motion, certain dynamics at play that have a solution, and that the way that you get to a probabilistic understanding of the behaviors and the dynamics that this set of equations or this dynamics has is just by looking at the underlying Lagrangian and looking at the dependencies, not in terms of the states occupied, but purely from the point of view of the paths that the system takes for this period of time. And then that affords the opportunity, and I think this, I should have mentioned this when asked here, what's been happening recently from the point of view of the free energy principle. Then you say, well, what do you mean by a certain period of time? Well, then you get now to the separation of temporal scales. So you have this notion now where you can understand the paths, the trajectories, the dynamics of this thing that is defined by a Markov blanket for this period of time. And then you say, well, let's make the equations of motion drift at a slower temporal scale. And then let's repeat the game. And how will we do that formally? Well, we'd use the renormalization group, or the apparatus of the renormalization group. And then what you have is now, you've now freed yourself from the Markovian constraint. So the universe as now articulated in terms of these series of random differential equations, where the random differential equation at any one level supplies the control parameters or the parameters of the equations of motion for the dynamics at the level below for a period of time, means that you now have the opportunity to look at how the realization of a free energy principle, say in terms of active inference, at one level is deeply, literally contextualized in a hierarchical or renormalization sense by exactly the same formal dynamics at the level above. So now we've come back to evolution. Now we've got a slow process. In fact, that's a little bit grand. Now we've got, let's make it slightly simpler. Now we've got a nice mathematical distinction between inference and learning. And I'm focused on that because clearly many of your viewers will be watching the machine learning and advances in that field. And what this brings to the table now, this implicit separation of temporal scales, is quite a fundamental difference between inferring and learning. And immediately tells you that to optimize the weights of a deep neural network or the parameters of variational autoencoder or generative adversarial network, you have to do it after you've done some data assimilation, after you've done some inference. So because you've got the separation of temporal scales, both at each scale, exactly the same principles apply and can be both formulated in terms of the free energy principle or self-evidencing, just maximizing the marginal likelihood at that level. But the connection between the two now enables you to think about how learning can contextualize inference and how inference supports learning. So by inference here, I simply mean optimizing beliefs or maximizing the marginal likelihood of Bayesian model evidence or its elbow or its variational free energy bounds with respect to belief distributions or probability distributions over things that change quickly, states of the world. So the kinds of things that you would do, you would need to infer when doing surveillance or doing, speech understanding, or indeed in an active inference sense, speech production. As opposed to those things that fluctuate slowly, which are the connection strengths, the weights, the parameters, the laws, the contingencies that are in play in this particular context. Noting this, there's going to be another level above, which is a slow change in the context that you can learn, and then you can start to understand right from the Helmholtz machine right through to amortization. Notions of learning to infer is this optimizing the slow process to make the fast process optimal. And as such, noting that the way in which you optimize the slow stuff depends very much on having some optimal inference scheme or data assimilation scheme at the fast level. Pursuing that argument, it also tells you, well, the stuff all the way down and stuff all the way up in terms of separation of temporal scales. So you naturally now start to ask, well, what's the scale above the learning? And this would bring us back to this evolution and model selection and structure learning. How many nodes, how many factors, what's the actual structure? Do I use a convolutional neural network? All of these are structural considerations that you could use, for example, a genetic algorithm or a Langevin-assisted MCMC at a very, very slow timescale to now optimize the very structure of your variational autoencoder that's doing the learning to infer, that's enabling inference at a very fast timescale.
That leads to an interesting idea. So, having different timescales for different levels of the structural learning, and I don't know if that's been tried out yet, but I think it's definitely worth trying. I think I have a different question though about the paper, and thank you for that exposition. It was very helpful. One thing that's kind of occurring to me now is that, again, the concept of the Markov blankets are still, fundamental, and one, like, perhaps concern, I don't know if I should say concern, that I had with the paper is the way in which it formulated the Markov blankets, in terms of the curvature of the surprise being zero. Like, at least, you as people may remember, the sensory sets are those sets which the external world can control and you can view, but you don't control. And your active states are the ones that you can control, not the external world, and the external world can view them. And so there are these sort of four regions. And in the paper, you define, ways in which, let's say, you can set various terms to zero, which mark the, the boundaries between those those regions. What I'm kind of wondering is, do they have to be zero? Like, what if this is generalized a bit to have like a degree of active stateness and a degree of sensory stateness, and there was kind of a more smooth boundary between these? What would happen? I mean, would that give us any useful outcomes mathematically, or would it just get in the way and it's just more convenient to continue, zeroing out certain elements of the matrix? Like, has any thought been put into what if it was more of a matter of degree, and would that be helpful or just get in the way?
That's a very astute question. I think quite a lot of thought has been directed at that problem. Whether there have been any useful answers, that is another question. So just if I can paraphrase your question, because it's, I think, a really important one. What you are saying is that before we make any moves in terms of understanding the dynamics of things that persist in any given context, we have to define thingness. And in this particular construction, we are defining thingness in terms of sparse influences that underwrite conditional independences. So the zero elements that you were talking about there are absolutely crucial in defining the thing in a crisp and unambiguous way via conditional independences. That just technically, for those people who like thinking in these terms, and zero entries in the Hessian of the system when where the Hessian is the curvature or the second order derivative of the likelihood, effectively. And then the big question comes then, where do these zero entries come in that define stipulatively thingness in terms of conditional independence? If it was the case that you could not establish conditional independence between the inside of something and the outside of something, then there is no way of really separating the states that into inside and outside. So the game then, and the delicate game, and the one which has been receiving attention in the last few years in the purely academic philosophical literature, but also in the maths literature, is exactly this question of how does sparse dynamical coupling, mainly I can't actually influence you because you two are too far away or you don't have the right kinds of receptors, how does that translate into these zero entries? And then your question is, well, okay, do we have to be commit to exactly zero? Can we actually now have a little bit of wandering away from these hard constraints? Now, mathematically, I wouldn't want to do that because, as you say, it's much more convenient just to sort of identify zero entries in the Hessian and implicit conditional dependencies under some sparse coupling. So what I would say, I've got two levels to the answer. First of all, the zero, the absence of any conditional or the presence of a conditional independence is not a terribly restrictive or magical requirement, in the sense that it is just a reflection of sparse coupling. So I think that you would put the question really not to the dependencies and the Hessian, but really to the notion of an influence diagram that was predicated on a set of differential equations you thought was appropriate to describe this universe. Now, if you think universes have all-to-all influences, so every state of this universe can, in a dynamical sense, simply the sense of a Lagrange equation or a random dynamical system, influence every other system, then you will have a soup, and you may have interesting structure with it, but that structure will not pertain to anything that can be separated from the universe because everything's connected to everything else. So you start to ask,
well, can I jump in here?
Sure.
Because I think to a degree, much of the universe, and just kind of leaving aside, okay, I'm sure there are some, horizons at which locality horizons, whatever, but I think that on the scales of, say, human beings, we are in a soup. I mean, we are influenced. It's just those influences may be very, very small, almost epsilon in a sense. And that's what kind of worried me about it, is that, look, I think I know that at least in terms of physics. There is this soupy influencing of everything kind of on everything else. And so what happens if we're dealing instead with mathematics that has these sharp, zero boundaries? Is it going to be an accurate reflection of the more soupy, albeit still exponentially decaying, couplings?
Perhaps I should just ask you, I mean, certainly it is the case, with 6 degrees of separation, that there is a vicarious influence that will almost certainly be non-zero. But did you mean those vicarious influences? Because for me, of course, the whole notion of a vicarious influence through something else immediately invokes the notion of something, which means another Markov blanket. So certainly there can be indirect influences, and I'm not denying that, but just in terms of the physical, it's probably a bad word to use, but just in terms of the functional form of the differential equations, that will evince this vicarious all-to-all coupling via other states. Do you think that that most universes are sparse or not sparse? So the assumption is here that it is the sparsity that endows this radical system with structure, and in fact, the exception is a non-sparse connection. And then the question is, how do you get soupy mutual influence amongst all the constituents or states that constitute that radical system? So, if you didn't have that kind of sparsity, you would never have a hierarchical organization, in the sense that a hierarchy just is the lack of an influence that transcends more than one level, say in a subsumption hierarchy. In physics, let me before I forget, the other half of your argument is much more accommodating of the epsilon and the fuzziness, which brings us to sort of the notion of wandering sets and back to the this notion of separation of temporal scale. So how long is it nearly zero, or almost zero? Acknowledging that at some point it's going to be not zero again because things change. So that I've sort of jumped to the second half of the argument, but I'm interested to try and bring the really important, from my perspective, notion of sparsity back into focus, and say that it is not unremarkable to assume lots of zeros in influence, because we do that all the time when we write down any differential equations, just by omitting one variable in a state vector from the function that defines the equation of motion, the flow operator. As soon as you omit one of a universe of variables, you've introduced a zero in that sparsity, in that dynamical coupling.
Maybe this is really the heart of abstraction, which is, even if there are these very tiny soupy couplings, we can abstract. We can just treat those all as zero, eliminate them, and still that abstracted model reflects, emergent behaviors of the things, if you will, of the universe, really, that we're trying to model. And I think that's kind of this duality between the fact that we may have a soupy substrate and yet still discrete sparse behaviors emerge on top of that soupy substrate.
Yep.
Is probably one of the greatest mysteries for me. So I don't know the answer, but I just wanted to get your thoughts on it, about.
Well, I mean, I think that's a very important question. I've seen it asked, interestingly enough, in correspondence with people who are sort of trying to look at the origins of life and are trying to understand the emergence of biotic self-organization, and from many different perspectives, from the kind of approach that people like Kate Jeffries or Jeremy England might take, right through to theoreticians try to reproduce organic-like self-organization by reproducing, the vents at the bottom of the sea, primordial soups in structured containers afforded by these vent one thing which struck me in these arguments was the notion of emergent behavior that had this self-replicating aspect to it. From a dynamical systems perspective, the emergence of attractors that have a Poincaré section, you get sort of a cycle of life emerging, was the notion of shielding. The notion of protecting yourself from the influence of other things. As a way of understanding enzymes, for example, or ways of understanding the physical structures that lead to sort of cell-like formations. That notion of shielding comes back to the possibility that it is the emergence of sparsity and the construction and the self-construction and the autopoiesis of sparsity that underwrites a Markov blanket building system that is necessary for the kind of structured self-organization that that you're asking the question about. So literally, how do we move from a primordial soup to a set of discernible things? And the answer seems to be, from what I'd read, it's the emergence of certain autocatalytic structures to actually sequester and shield certain sort of chemicals or processes from other chemicals, and in the shielding thereby emerge from my point of view, the Markov blankets. So again, we come back to the notion of sculpting structure by removing stuff. In this instance, it's removing connections, creating the right kind of sparsity where structure actually emerges from the soup.
Point of interest, Karl, could you define, I'm really interested in your definition of self-organization and emergence, and also, do you think it's a useful distinction to have this notion of strong emergence and weak emergence? Could you just give us your take on those?
I could if I was more of a scholar, but I'm going to have to ask you to define strong and weak emergence.
Well, it's all about reducibility. So, I mean, I think weak emergence is a kind of emergence where the emergent property is amenable to computer simulation or, similar forms of after-the-fact analysis. So, like, the formation of a traffic jam. And strong emergence is this notion that the whole is something more than the sum of its parts. I mean, I was actually going to ask you a slightly related question about substance dualism, right? Which is that, some philosophers have this notion of the mind not being reducible to its component parts. So a materialist, for example, or a physicalist would think that. Do you think there's a kind of parallel with this notion of strong emergence and the irreducibility of our mind and consciousness to the constituent components?
Right. You're clearly more versed in these fields than I am, so I'm not going to pretend to give you...
I highly doubt it, Karl.
In this instance, you know a little more than I do. However, I get a sense if you wanted a proper answer to that question, I think it would probably come back to this this separation temporal scales and posing that question to the kinds of systems that would constitute a renormalization group, and say, is there anything that emerges at one level that could be abstracted from the level below? If you could find an answer that satisfies you in terms of the difference between strong and weak emergence, by looking at a system that has that renormalization property with the separation temporal scales, then I can tell you what the answer is. Unfortunately, I don't know, because I'm not sure what the commitments of strong and weak emergence are. But certainly, it would be impossible to understand one temporal scale or one level without writing down or simulating or understanding the level above and the level below. So in that sense, I suspect that there might be a strong emergence in play here. The reason I mention that is that of course is the get out, and it's the mechanics that you would appeal to resolve the the sparsity or the Hessian equals zero problem. So it's clearly the case that even in a soup, or a soup that transiently, or a collection of well-defined cells where there is this shielding and sparsity of influence that protects or insulates the internal dynamics of, say, a cell from the external milieu. At some point, there's going to be cell division. At some point, there could be some metamorphosis or transformation or phase transition where it is rendered soupy again, and you would need a different set of Markov blankets. So how do you go from one cell to two cells? So you've got this notion now of wandering sets. So the Markov blanket partition was nicely described into as a partition into internal and external, and the intervening active and sensory states that mediate the bidirectional influence of the inside and the outside. That partition comprises a subset. So what you're talking now is about the possibility of wandering sets in the sense of Markov. How on earth can a set wander when it is defined stipulatively in terms of sparse coupling expressed as a random differential equation or a Langevin equation? Well, it can change if you say, well, this set of equations of motion is only in play for this amount of time, and then in the next chunk, we're going to change the parameters of the equations of motion and bring in other states. And as soon as you bring in other states into your flow operators at a slow time scale, you're now destroying the old sparsity structure, replacing it with a new sparsity structure, or possibly destroying the sparsity structure altogether. So I think that would be the way that you put epsilon back into the game. But actually, more than epsilon, actually allowing for the fact that there is a certain scale of organization in space and time that is superordinate to the microscopic dynamics of your level of inquiry, over which you will now have a reconfiguration of the Markov blanket. So things will look as if they're reorganizing. So at what level is self-organization happening? You can't answer that question. It's at all levels, because the context of self-organization at one spatio-temporal scale depends sensitively and critically on the parameters that define the initial conditions and the flow operators that are inherited from the scale above. And likewise, the scale above has to conform to exactly the same dynamics. It has to have things in it.
Fascinating.
So I think that's how you would get out of the getting to a more plastic, semi-Markovian universe, a biological universe. You'd start to answer the real questions of autopoiesis. I feel a little bit naive in saying that the free energy principle does autopoiesis in retrospect, because autopoiesis has a lot more to it, and it's exactly what you've been talking about. How do you get these self-preserving? How do the fast microscopic dynamics create the context for there to be a self-assembled Markov blanket that entails the faster? These are really deep questions.
Indeed. It's another example. Actually, we've spoken to cyberneticists like Professor J. Mark Bishop, and he introduced us to lots of stuff about autopoiesis. But I've just got a bit of an eye on the time, so we've got a couple more questions to get through. But that was absolutely fascinating, Professor Friston. But I'm not sure if you're familiar with Ilya Sutskever. He's the chief scientist at OpenAI, and he became embroiled in a heated Twitter debate a couple of weeks ago, where he asserted that large language models, the likes of GPT-3, might be slightly conscious. And of course, I'm speaking to an authority on consciousness here. When you spoke about consciousness, actually, recently, you said, and I'm quoting, the proposal on offer here is that the mind comes into being when self-evidencing has a temporal thickness or counterfactual depth, which grounds inferences about the consequences of my action. In this view, consciousness is nothing more than inference about my future, namely the self-evidencing consequences of what I do. I think this is a fascinating way to put it, and Keith told me earlier that he thinks of consciousness in a very similar way. But the one thing that is missing from this discussion, in my view, and by the way, we're speaking with good old David Chalmers in a few weeks' time, but what about the phenomenological characteristics of consciousness?
Right, so we've got a couple of minutes to do that. That'll be fine. we could get David to watch this. Give him my very best wishes.
Oh, we certainly will. And by the way, if you have any questions as well for us to ask David on your behalf, I think that'd be very,
well,
very
you should
exciting
ask him everything you've just asked me and see what he says. I love David Chalmers, and I also like the way he responds to some of the more technical questions that he gets. And his response to this one, I think, would probably loop in the notion of the meta problem or the meta hard problem, which put simply in the words of Andy Clark would be, why is it that certain things, i.e. philosophers and people like you and me, puzzle so much about our qualitative experience? And it may sound a strange question, but it's a very revealing question. It simply means that if you subscribe to the notion that we are inference machines, we are built to actively self-evidence, then you are saying that we entail a generative model of our experienced world. And if we have a generative model of our experienced world and we can talk about and puzzle about qualitative experience, we must also have a hypothesis that, first of all, we are things. Second, we are having a qualitative experience with the alternate that we are not, which of course then provides a really simple explanation as to why philosophers love things like brain and vats and the zombie arguments, irrespective of whether they are useful thought experiments. The very fact that you can get something like David Chalmers, as a young man, talking about zombies, and people listening, tells you immediately you've come across a certain sentient artifact on Earth that has got a generative model that can entertain the counterfactual hypothesis that they don't have qualitative experience. Now, you may be asking, well, why is that so interesting? Well, it's interesting because it tells you immediately that these kinds of sentient creatures are showing a sentient behavior that necessarily requires the ability to hold counterfactuals in mind. And I mean, so now I'm trying to work back to your introduction of the notion of the temporal depth, and something that Anil Seth might also complement with counterfactual richness. So the argument here is very, very simple, which I'm sure you know, but probably worth rehearsing. So if you had a program that could understand language, then what would be the requirements of the underlying generative model that it was using to infer to make sense of the auditory stream, to infer the meant word? Well, for it to be conscious, it would actually have to be able to ask questions. So it would also have to be able to speak. So that's the first inactive move that you see with the triple E's since the turn of the century. So we're talking about systems that are not just sentient in a passive, sessile way, but have sentient behavior. So there has to be behavior. So your language understanding machine has to be able to do something. It has to be able to move or ask a question. And of course, then you ask, well, what are the best questions? Well, those are the ones that comply with the principles of optimal Bayesian design. And then you can trace that right back to things like, or from my point of view, articulate that as a special one part of expected free energy. But the key thing here is that the program, the scheme, the algorithm has to be able to move, ask a question, interrogate the world, perform an experiment on the world to do self-evidencing. If it's doing that, then it has to have a generative model of the consequences of its moves. So that's the simple and big move here, that just if you want to talk about sentient behavior, you are necessarily, if you subscribe to the fact it all entails a generative model, then you're talking about things that have generative models of the consequences of their moves, their behaviors, their choices. Because those consequences are in the future, they are necessarily acquired, that the generative model necessarily acquires a temporal depth. So just saying that I have an understanding or an internal model, if you're a psychologist, it could be a simulation model. If you're in motor control, it could be a sort of a forward model. But most generally, just having a generative model of the consequences of action means you've got a temporally deep generative model. And notice it's the consequences of your action. So there's an implicit agency that suddenly comes into focus. So now you can use the word agent. As soon as your generative model contains the consequences of action, then you can use the word agent. You can't do that.
Could I just pick up on this a little bit? It sounds a lot like you're saying it must be a closed loop process. And this rather leads back to, I know you were talking about things like AIXI and some of the information theoretical conceptions of intelligence. And those conceptions also rely on this notion of an agent acting in an environment. Does that seem in any way, I don't know, it feels a bit anthropocentric, doesn't it? To use that notion of consciousness or even intelligence. Is that a good framing, do you think?
Yeah, I hadn't quite got to consciousness at this stage, which will be certainly an anthropomorphic or centric notion, but I think in a way that, if you like, celebrates that anthropomorphic aspect. All I said at the moment is that if you want to talk about sentient behavior, before you get to consciousness, you've got to have temporal depth. And crucially, in having consequences, there can be more than one outcome to any act. So now you necessarily have a counterfactual aspect to the things in your generative model, which brings us to my point before about, perhaps the best thing that David Charman's presents from my point of view is an existence proof of a sentient creature that can have counterfactuals of a certain kind where it's not being able to have qualitative experience. But this is an example of a counterfactual hypothesis. This is a gift of very, very sophisticated systems that are probably a long way down the path to ultimate simplicity in terms of evolution, or at a very, very slow time scale. So it's a real gift to be able to have these counterfactuals. Andy Clark would argue that just qualitative experience is also another counterfactual. So there will be a grandmother cell in your prefrontal cortex that fires when it says, "Oh, I'm having the qualitative experience of seeing red." And it has to be like that in order for you to be able to be aware of it. But using words like awareness now, and indeed self-awareness. So qualitative experience, first of all, underpins self-awareness, which would be a qualitative experience of selfhood. So, there are layers upon layers that you're talking about here. Each one of them has to be manifest in the generative model. So the first thing is that everything I've said so far, in terms of agency, could be applied to a thermostat. So is a thermostat conscious? Probably not. So what kind of system, more complicated generative model, would you need to have in place before you could think, yes, possibly that could be conscious? Well, the first one is the depth of planning. So a thermostat just does not look beyond the trajectories implied by the generalized motion and that's the gradients that are at hand. It can't see half an hour into the future. It just knows that things are going up or going down in the moment. Very short term sort of path formulation or generative model. But things like you and I can go and have much greater temporal depth, and then we invert the notion of planning, and then I repeat, selecting amongst a number of different counterfactual outcomes, evaluating them and choosing one. You get into issues of free will at this stage. But still, you can imagine writing a robot, equipping a robot with these kinds of generative models, and people have done this. Would you call that sentient?
Right.
No. Then you have to have the hypothesis that it's you doing that and you in different states doing that. And then you have to say, well, why? Sorry, I'm rushing because I can see you're anxious to move on to the next question. I just wanted to make it clear that it's a very special kind of generative model that even has selfhood, let alone aware that it just has selfhood, and even more rare to actually have somebody who worries about these things and not having the selfhood.
This is fascinating. But you are a computationalist then. You do believe that humans are independently conscious. So first of all, I think what you're saying, if you are a computationalist, is that if we could recreate all of the stuff that you're just talking about, so forward reasoning and planning, etc., that we could recreate consciousness in silico.
Yes. I see no reason why you couldn't create an artifact that was sufficiently similar to you and me, that would that qualify as being conscious. Yeah, that I am.
That's fascinating. Because the cyberneticists typically think that it's an emergent property and its computation is observer relative, so it couldn't possibly exist in isolation. And then that leads on to assertions of panpsychism, where consciousness must therefore be in everything.
Well, can I ask for a clarification? Because I think I'm a computationalist as well. So suppose we did create an in silico, chip and some software that had the depth of counterfactual planning, of temporal planning, that could in fact evaluate its own actions and could even evaluate at a meta level, the computations that are going into that evaluation. So that's sort of full stack, almost a full recursive stack there. Would that thing, because a lot of times what I read from, Chalmers or others is a question of feeling, like what does it feel like to be conscious, right? And so would that thing, in your view, feel like something? Would it have the qualia of experience that we do?
Yes, but you'd have to write it into the generative model. So you'd have to write the different feeling states as hypotheses about how am I feeling at the moment. And then it would use, or I would use, or you would use, all the messages and the belief updating and all the planning and all the estimates of uncertainty that attend that planning. And that's quite key, actually. The precision or the estimates of uncertainty start to take much, much greater roles in terms of the heavy lifting of the belief updating, the higher you get in the hierarchy. So I am feeling in this way. I am aware of my selfhood. I am having this qualitative experience. These would all be hypotheses that were recognized in a good old-fashioned variation autoencoder way of everything that's going on below, crucially including interoceptive feelings, or states of your battery, your blood sugar, and all of that good stuff.
Okay, so I think if I understand you correctly, and this is pretty cool. So the feeling is actually a knowledge of a certain, activity or trajectory. Like that is the feeling is in fact a knowledge.
Yep. Absolutely. Well, you could even say that the instance of the feeling, the realization of the feeling, is the inference in the context of a knowledge structure that just is the generative model that has representations or slots that have a semantics of I feel like a self, I feel unhappy, I feel anxious, I feel in love, whatever it is. That is the best sense making, the best hypothesis or explanation in a simple but not too simple way for everything that's going on. So feelings, including things like pain, and this is quite an important. So this is not just a philosophical nicety. It really matters in the treatment of chronic pain when you're trying to identify the locus of pain and what is pain. It seems as if pain is a hypothesis that certain people bring to the table as the best explanation for all of their experceptive, interoceptive feelings.
Fascinating.
I want to bring in this subject of subjectivity, because when we do try and formalize things, and I know Keith is smiling because we were just speaking with Kenneth Stanley, and he has a wonderful book called Why Greatness Cannot Be Planned and the Myth of the Objective. He thinks that formalizing things actually blocks us from discovering interesting stepping stones in life, and even in the frame of our thinking, it actually stops us from discovering new interesting knowledge. And this is interesting in your formalism. So there was a chap called Arthur Eddington, the notorious astronomer and physicist born in the 19th century, and he spoke about subjectivity in science. And I think his point was that science only tells us a sliver of what's really happening in the world around us, and we should be a lot less arrogant in our claims to understand it. And Kenneth Stanley says that we've been too focused on objectives, and the broader story is that he thinks society and institutions are scared of any subjectivity, or perhaps, you might think of it as system one thinking. So we always try to verbalize and understand everything. But similarly to what you were just saying about in respect of agents and the conscious experience and subjectivity, it doesn't feel very objective anymore when you're talking about emotions.
Yes. The mention of Arthur Eddington was very prescient for me. So that's how I got started in this game with his book, Space, Time and Gravitation, that my father made me read. So that's
Wonderful.
You know what's fascinating about that? I got started in philosophy because I read his book, The Philosophy of Physical Science.
If only he knew. His family would be very proud of the impact that he's had on us all. A century nearly. It is now, but almost a century later.
Absolutely. But do you think there's a bit of an interesting contradiction there in yourself, that as scientists, we struggle to formalize everything, and you can't even get funding for a grant unless you have a clear hypothesis and a clear understanding of what you're doing, and your papers have no value unless you have a clear formalism of what's going on.
That was the spirit of the argument, which I certainly concur with. So I don't see any real debate or dialectic here. I mean, this is just simply a problem that we were talking about before, in terms of the good scientist being able to build an apt hypothesis space where no one else has ever gone before, and then do your self-evidencing or evidence-based science. But clearly the problem of building that hypothesis space, that to my mind is unresolved in the physical sciences. Scoring any particular hypothesis, absolutely no problem. That's just estimating the marginal likelihood of the model evidence, or some variational bound on it. And it can be, as difficult a hypothesis space as you want to consider. But building it in the first place, I think that's that is the outstanding problem, both practically and philosophically. And you have to ask, well, are there any examples where it's been solved? Well, yes, natural selection has solved it. So it's used a particular way of exploring in a structured way, using, say, bisexual reproduction. And that sort of gives you clues as to how you might create, literally do lateral thinking or inventive thinking, having ideas and hypotheses that no one ever has had before. So, I think that question, if I read it properly, just speaks to a really challenging, exciting and practical challenge, not just for science, but people trying to build sentient artifacts that now have, in a principal way, the ability to actually have new ideas and to test these new ideas out. And I should just add that one example of these new ideas is that I am a person and I'm happy or in pain. There's nothing, I don't think there's anything particularly magical about the kind of constructs we talk about in philosophy of selfhood and consciousness and self-awareness, and the psychophysics of visual perception. It's just having these new kinds of hypotheses. Perhaps they're not so new in terms of selfhood because of the acculturalism that we're talking about, and the fact that Mum talks about me, and it's a very viable hypothesis that explains a lot and actually makes my data foraging or my epistemic foraging much more efficient. Just to simplify the world. Oh, I am a person, and Mum is a person. There are two selves. That hypothesis, perfectly fit for purpose, maybe complete rubbish, I don't know, but it's a hypothesis that seems to work really well. And when you generalize it, oh, there are other persons, self. I seem to be in a universe populated by selves. This is a hypothesis which is reaffirmed through gathering the right kind of evidence through communication, afforded, of course, by language and other aspects of it, cultural evolutionary psychology, that again speak to the sort of separation of temporal scales. But quite within this, quite naturally, selfhood arises, and one could argue philosophers also will flourish, and we can have conversations about the hard problem, ultimately the meta hard problem, as he will do. But it all rests upon, at some level, at the highest level, new hypotheses, simpler, better hypotheses, being tested by some artifact or some Markov kits.
The thing that fascinates me, though, is that with the FEP formalism, you were saying before about self-evidencing and finding our eco-niche. And when we do talk about, when we introduce subjectivity, it feels much more divergent and much more random. And that's what Kenneth Stanley says. He says that any formalism is convergent, and in order to be divergent, we need to embrace subjectivity. And it feels like emotions are the human form of subjectivity. So that kind of, in my mind, that makes this process feel much more random and divergent than perhaps the formalism would make us think.
Again, I don't feel I can't quite get a sense of a dialect. I don't know who would disagree with that. It certainly is the case that finding your place, and we actually demonstrate this in silico using cells that differentiate. Finding your place under a shared narrative or generative model amongst a population is a free energy minimizing solution, and it necessarily leverages or relies upon subject-specific realizations that are contextualized by what the realizations another subject has. So you can certainly argue that subjectivity, that subject-specific expression of your sense-making, active sense-making, is a necessary part of the minimization of the joint free energy of a number of free energy minimizing systems. Even to the extent, this is basically the holy grail and taken as read in things like computational psychiatry. So, if you want to use let's say the active inference process theory to understand and phenotype people who might or may not have schizophrenic symptoms, or may not show addictive behaviors, or have this kind of autistic expression, then what you can do is you can use the complete class theorem to say, well, look, in this game that I'm going to give you, there are the complete class theorem tells me that your behavior will be Bayes optimal, whatever you choose, under some priors. What I want to know is, what are your priors? So that means for every person, every subject, there is a unique set of priors that characterize their behavior under ideal Bayesian assumptions that can be read as active inference. So the job now is to try and identify what are this person's priors, and then use that to test hypotheses that you're this kind of person or that kind of person. So try to find some systematic structure in the belief structures that each subject brings to the table.
Yeah. Before we run out of time, I do want to ask you the perennial free will question. So, I think, and correct me if I'm wrong, but I think you believe in a universe that's unfolding according to these deterministic, albeit stochastic, but deterministic, flow equations, differential equations. And so the universe is deterministic from that perspective. And so is that correct? Would you agree with that?
Sorry, yeah, just technically, you have random fluctuations in a random dynamical system, so you don't get deterministic chaos, but you can certainly get stochastic chaos. Absolutely. And just interestingly, it is becoming clearer that things like you and me may well have particular flows that are almost deterministic, even if the outside is a bit random.
Sure. Yeah, and I would even say it's entirely possible that those stochastic fluctuations are themselves highly chaotic, deterministic systems, or even if they are pure chance, they're of the form of a chance that's, not controllable. It's just, it's just sort of this truly random chance. And so in that context, a lot of folks have a lot of trouble imagining how we can have quote unquote free will. From my perspective, free will is simply that an agent evaluates a set of inputs and sensory things and has an algorithm that then determines, what actions it's going to take, based upon that. And if you had put in different sensory inputs, it might have chosen a different pathway. Like I'm talking about sort of degrees of freedom, if you will, is free will. Almost the same kind of concept, I believe, that Daniel Dennett espouses. So I'm curious how you see free will in the context of a universe unfolding either purely deterministically or deterministically with stochastic, variation.
I think I see it almost exactly the way that you expressed there. just to make the point that the fast stochastic fluctuations, of course, can also be just expressed at a faster time scale using the renormalization grid. So you don't even have to say, I'm committed to stochastic as opposed to a deterministic chaos with a correlation dimension of greater than 10, for example. You don't even have to do that once you allow for the separation of temporal scales. So you can talk about a universe that is, it's no longer Markovian because of the separation of temporal scales, but it certainly has the opportunity at one given scale to have deterministic chaos. And I think just in saying that, you're perfectly licensed to talk about free will. In fact, it would be difficult to imagine anything that plans and selects one of a number of ways forward, those counterfactuals we were talking about before, that could not be construed as selecting and thereby manifesting, evincing at least a minimal kind of willfulness, in the sense it has to do selection. One could argue, well, does that mean that natural selection is selecting you willfully? Does it make a choice? Does it have free will? I'm not sure about that, but certainly if you have a generative model that sees itself doing its natural selection of the best counterfactuals about what to do or say next, then there is that would, I think, be part of this sort of minimal selfhood that would be undeniably a representation and an inference and a recognition of my free will. And if I was able to infer that you were sufficiently like me and presumably had the same kind of generative model, I would also infer that you had free will and you would behave as such, and I would secure that evidence by talking to you or just watching you. And I would also leverage it. I'd also use that as theory of mind to infer your intentional stance, because I see you behaving in a way, and if I behaved in that way, I would have selected that plan, and therefore I would have made that kind of choice, and that would tell me the kind of person you are. So it brings us back to the priors that characterize all of us. In this instance, if I can infer you very accurately, we share the same prior commitments. We have very, very similar generative models.
Okay, thank you.
Amazing. Professor Karl Friston, thank you so much for joining us this afternoon. It's been a pleasure.
I've enjoyed myself greatly. Thank you very much indeed.
Wonderful.